Galileo was born in Pisa in 1564. He was the first of six children of Vincenzo Galilei, a musician and scholar. In 1581, he entered the University of Pisa to study medicine, but later on in his life, he realized that he did not want to study that and continued his life in mathematics. In 1583, he made his first important discovery describing the rules that govern the motion of pendulums, while also in 1609, Galileo heard about the invention of the spyglass, a device which made the distant objects made closer. Galileo used his mathematics knowledge and technical skills to improve upon the spyglass and built a telescope. With this invention, he was able to look at the moon through the telescope and make his first astronomy discovery. While looking on the surface of the moon, he realized that it was not smooth, but mountainous and pitted, as was Earth. He subsequently used his newly invented telescope to discover four of the moons circling Jupiter, to study Saturn, and to observe the phases of Venus, and to study sunspots on the sun. Later on in his life, Galileo also began to invent many inventions, such as using a water clock to determine how time has passed, and also using a pendulum. During the water clock invention, he measured the time it took for the ball to roll down a known distance down the inclined plane. After many trials, he observed that the amount of time it took for the ball to roll down the entire length of the ramp was equal to double the amount of time it took for the same ball to only roll a quarter of the distance. In other words, if you doubled the amount of time that the ball was rolling, it would travel 4 times as far. So while in this invention, he was able to determine how much time had passed from the time that it took the ball to roll down the ramp as compared to how much time the water took to fill a certain container up, or how much water was being contained.
Galileo wanted to study the relationship between acceleration of free-falling objects and gravity. The main issue was that free-falling objects fell too fast for him to time with the technology available. He figured out that using an inclined plane would slow down the effects of gravity. The idea was that free fall was equivalent to a completely vertical ramp, so a ball rolling down an inclined plane would accelerate the same way as a free-falling ball would. Then, using what is called a water clock, he could find the time. This allowed him to use the relationship between distance and the weight of the water that falls in the time it takes the ball to reach the end of the inclined plane. Measuring from various heights and angles, he was able to find that the distance covered is proportional to the time squared.
The construction of the project was fairly easy. We cut out 3 different pieces of poster board, 2 of which were 80 centimeters long and the other 30 centimeters long. The 2 80 centimeter pieces were used to funnel down the ball so it would not go off of the ramp. The 30 centimeter piece was used for the height of the project. Although the 30 centimeter piece was meant to be the height of the project, it ended up standing at 27 centimeters. This is because the piece was cocked at an angle, which made the overall height lower than the hypotenuse of the project. For the water clock, we used a water bottle, which we cut off the bottom and poked a hole in the lid. This allowed for a good amount of flow to go through the top of the lid. With some minor adjusting of the hole in the top of the lid, we got the flow rate just right. To catch the water, we used a beaker, and to measure the weight of the water, we used a triple beam balance. In testing the project, we had a 3-man team. One controlled the water clock, one let go of the ball, and one wrote down the grams of the water.
And when Kyle lets go of the golf ball on the left, Domminic lets go of his finger. And once he does this, a certain amount of water is released into the beaker. And as soon as the golf ball hits the bottom, Domminic will put his finger back over the water. And then it's not shown in this video, but we would wait on a triple beam balance, and we would return it back to our our bottle. We wanted to ensure that there was the same amount of pressure in the bottle, because we found out that if it was a different amount of pressure in the bottle, it would release the water slower or faster depending on how much water was in the bottle at the time.
Some errors in our project could have been the timing of the water, the friction due to the poster board because it had ridges on it, and the measuring of the water on the triple beam balance. To fix these problems in any future project, we could have used wood instead of poster board and sanded it down to reduce the friction of the board. Had a electronic scale in which we could just view the number instead of having to adjust the balance. And with the water clock, I'm not quite sure. Maybe have the person controlling the water clock let go of the ball too.
As you can see in this Excel spreadsheet, what we did is we got the 4 distances. We had the 20 centimeter length, the 40, 60, and 80, the full length. And what we did was we took an average of 10 times that we did the experiment. In the left-hand column, underneath trial, we have the full weight of the beaker. In the second column, what we have is the subtracted weight from the weight of the beaker, which is it should be 324.2 grams, and we subtracted it from the weight of the water, and then the average time is in the last column. It's for the first one, it's 13.11. On the second, it's 14. On the third, it's 20.46. And on the final one, it is 28.69. And these concluded our our water clock experiment data. And what we did after this is we plotted the points. But what we did was I put, to get the certain ratios we need to get the graph, I put our quarter length over our full length. And I basically did whatever I did was whatever length it was, I put it over the full length of the ramp, and that gave us smaller numbers enough to put on the graph. Then after we got all the ratios for our ramp, what we did next was we found the ramp angle, and how we did this was we took the cosine theta equals to x over r formula. We plugged in our 78.33 for our length of the ramp. And then what we did next is we got our 80, which was our hypotenuse. And this let us, we took the inverse cosine of x over r, which was 78.33 over 80. And it came out to 14.844 degrees. And that showed us our angle of the ramp. And as you can see here, it was kind of a little different from as you can see in our video that they demonstrated our experiment. Our triangle is a little bit off because it's not 30 centimeters in height. It's actually 27, because the way that the ramp was built, it came out to be 27 centimeters high. And we could have fixed this, but in conclusion, it really didn't hurt the project at all. We just counted for the 27 being our height instead. And also in the video, in the clip where they are showing you how our experiment was worked, can you fucking stop, babe? In the video where we demonstrated our ramp, you can see here that when Kyle on the left lets go of the... As you can... Oh, shit. And lastly, you can see our graph that we made. And it's not a perfect graph like most people's. It's a little bit off, but you can see where the 0.25 is where the ramp was at its lowest, and then with the lowest time. And then the orange dot where it was at the highest point at 1, and the full size ramp. But yeah, these are the equations that we got out of the from the ratios, and we plugged it in to get these coordinates, which is like it's 0.75 is at 0.71314, 0.5 is at 0.487975, 0.4569 at 0.25. But I mean, it's pretty self-explanatory. We use the quadratic equation to get this function that sort of maps our time versus length graph, which our length is our x, and then our time is going to be, or the time or the weight of the water would be our y value.